Okay, optimization example. This is in section 4.4, number 5. This is similar to an example we did, but it's not the same. You listening? All right. A box with a square base and open top must have a volume of 4,000 centimeters cubed. So the constraint that we have is that the volume has to be a certain number. And what we're trying to do is minimize the amount of material used, which amount of material is the surface area. Okay? So if you want to construct a little diagram, might be a nice idea. So I'm going to do a little box here. It's a square bottom, and we have an open top. So it looks kind of like this. And the volume is 4,000 cubic centimeters. And it's a square bottom, so let's put some variables on this diagram. I'm going to X there. And then, of course, with volume, we need the height as well. So let's do height. You can do Y if you want, but height represents height. We did this before. Okay? So the volume is 4,000, which means that 4,000 has to equal, what's the formula for the volume of a box like this?
X squared Y.
X squared, well, I'll use H because I used H there. X squared H, okay? All right, no problem. The surface area, this is what we want to maximize, so let's be careful with this one. We want to maximize the surface area. So I have 4 sides, right, and a bottom. So the bottom is going to be X squared, that's the bottom. And each of the 4 sides are going to be what? Yeah, XH. So there's going to be 4 of them. So I have X squared, which is the base, times the 4 sides, which are each XH. Everybody good with that? Okay. That's where you can start. 2 variables is totally fine, but you want to slam those equations together, get 1 variable only, which means that in this one we're not optimizing. Let's isolate for one of the variables. And do this. Let's isolate for H. Yep.
Could you do it with the other one and just take away 4x? Oh, no, never mind.
Could you isolate X? You could isolate for X. Now you're going to have square roots though. And you're going to have square roots in 2 places. So I would probably isolate for H because it only shows up 1 time here. But yeah, you could isolate for either of these variables and substitute. It's going to be different equations. You might not know which one's going to be easier to do calculus on, but yeah, if you see it just one spot, it's probably a good idea to just substitute that one. So this is going to be X squared plus 4X times 4,000 over X squared. Good. So we'll simplify, and yes, this surface area now is going to be a function of X. You don't have to write that, but now we're sure that that's just 1 variable, so it's really a function of X, which is what we're going for. So this is going to be X squared. All right, this X is going to go with one of those, so it's going to be plus 16,000 over X. With me there so far? All right. That's probably as simple as you need to go. You could do this, I suppose. You could do this X over X as an X to the negative 1. Using the power rule instead of the quotient rule might make you sleep better at night. So go ahead and feel free to do that. I would encourage you to do that. You guys see this? It's like all of a sudden it seems like small now, but maybe that doesn't help. Okay, fine. Okay, so we'll take the derivative now. So surface area prime is going to be 2x. Now this is going to be minus 16,000 x to the x to the negative 2. Or I'll put over x squared now. Yeah, x to the negative 2 is over x squared, which is just going to make letting this equal to 0 and all that maybe a bit easier. Okay, you good so far? Awesome. We're on the road. So any values for x that are restricted? X cannot equal 0 here, right? Now, is that going to be a valid option for minimizing the amount of material? If you have a box that's 0 units wide and 0 units long, That's not gonna work, right?
I guess if you didn't build anything, you'd need like similar material used.
Yeah, then your height would have to be, well,
It
it's
wouldn't
not
have the
gonna,
same volume.
you can't do 0 times 0 times some other h to
Oh,
get
yeah,
4,000,
it
so.
can't
So it can equal 4,000. So
Yeah.
x is not gonna be under
No
consideration.
box.
X, not one of our answers, okay? So now let's focus on the x that gives us a 0. So if I let this equal to 0, and I bring this negative term over to the other side, I'm just gonna do a couple steps at once here. I have 16,000 over x squared equals 2x. Multiply both sides by x squared, I get x cubed on the other side. Divide both sides by 2. I get x cubed equals 16,000 over 2, or up over here, x cubed equals 8,000.
What did you do?
8,000.
The 2 at the bottom?
I had a 2 up here. And then I had x squared down here.
Yes.
Okay, so what I did was I multiplied both sides by x squared, give that an x cubed.
Oh, okay.
Then I divided by 2.
Oh,
Good?
Yeah.
So is there a value for x?
20.
Yeah, 20. X equals 20. Technically positive or minus 20, but we don't want a negative length, right? So that doesn't. Sorry?
How could it be negative 20?
Oh, actually, yeah, because this is positive. If this was negative, you could have a negative 20. It would be negative. Yeah, sorry. This is positive. Squareds are the big thing. If you have anything squared, just reject the negative. But yeah, this one, because it's positive, this one has to be positive. Yeah, you're right. Thank you. Okay, so x equals 20. That's our critical number, our only one. So that's going to be the one that's going to minimize. Again, you could do a quick sign analysis to make sure. You could. We didn't really factor the derivative though. So that's going to be a little bit tricky to do. But you could test some value that's less than 20 and some value that's greater than 20. And, see what happens, I guess. So this is your derivative here, right? If this is 20, if x is 20, this is equal to 0. So if this was 0, that would be 0. Oh, that's a bad one. If it's 1, you have 2 minus 16,000. So that's going to be a negative, right? And then if you have something greater than 20, you're going to have a positive value. So that's, look at that. That does give you a minimum at 20. Okay, so just test some values with your derivative to make sure that's going to yield you a minimum, and yes. So the dimensions are going to be 20 by 20 by, you got to figure out what h is, so h is going to be 4,000 divided by 400, 20 squared, looks like, so h is 10. So the dimensions are 20, what are the units? Centimeters, by 20 centimeters, by 10 centimeters. And there's the whole question on your screen. All right, so number 6 says, a box with an open top is to be constructed from a square piece of cardboard, 3 meters by 3 meters. So this is 3 meters by 3 meters. So it's completely square. And this box is going to be made by cutting out a square from each of the 4 corners and then bending up the sides. You see that? So if I cut this out and these are equal squares, then we'll be able to fold along this line and this line and this line and this line. Then we'll have 4 sides and we'll have the base. See that? So the goal here is to find the largest volume that such a box can have. So think about it. If we cut too big a square this way, we're really sacrificing on our base area, even though our height is bigger. So do you want a small bottom box that's very tall? Or if we make this square quite a bit smaller, do you want a really large bottom box that has virtually no height, right? So somewhere in here will be the box with the largest volume. Okay?
I s-
So what we saying?
I thought that would have the same volume either way.
No, it won't have the same volume either way. No, it won't have the same volume. That's fair though, to think that it might. So again, what we want to do is we want to find out what this value is right here. Okay? So we're cutting a square, so it's a square, so how much do I cut? How big is that square? Literally our variable is x here. That's the unknown part that we're searching for. And again, we have to set up our optimization. So we're trying to optimize the volume. So what is the volume of this box? Well, it's going to be this length times this width times this height. But over here, from this diagram, I have to figure out what the length is going to be. This is going to be the length, right? You see that?
Oh, it'd be 3 minus 2x, right?
That's 3 units. I'm taking away this and this.
3 minus 2x.
So L is 3 minus 2x. Very good. And width, of course, because it's going to be square, it should be the same, right? 3 minus 2x. The height is what? Yeah, it's just x. Nice. So we've done the work already to make, we can now make a volume equation, volume equation with only one variable because of this work that we've done. So this volume is actually going to be written as 3 minus 2x squared times x. Exactly. Yeah. So I'll pause there. Anybody have any questions about that? Does that make sense? All right. So drawing diagrams, if you're not given one, probably a good idea. Okay. Labeling things, working that out. Okay. So now we need to optimize this volume. So might it be a good idea to multiply this out? I suppose you could. Or you could just do product rule, but you're going to have to do product rule with chain rule. So, I don't know. It's work ahead of time or it's work after. Usually expansion and gathering like terms is easier than doing some complicated calculus differentiation rules. So I would suggest probably just multiplying this out. That's going to be 9 minus 12x plus 4x squared, all times x, or v, which is now a function of x, is going to be 4x cubed minus 12x squared plus 9x, looks like. All right, so let's find the derivative then. That's going to be 12x squared minus 24x plus 9. Awesome. No restrictions on x, that's good. It's a polynomial. X can be anything. So let's find out where this is going to equal 0. And we might want to try to, now we could use quadratic formula. You guys want to try quadratic formula? It's been a while since we did quadratic formula. Hey, you want to give it a go? X equals, what? Yeah, so you can take a 3 out. Absolutely. Good idea. I was waiting for something like that. So if we just divided 3 out, that's going to be 4x squared minus 8x plus 3. That's going to give us some smaller numbers to work with. Awesome. Now this we could probably factor a little bit easier. But can I show you the quadratic formula? It's been a while. X equals negative b. Remember the song?
You don't have to note the 3.
I'm sorry, what? No, you don't have to note the 3 because I divided it out of both sides. It's gone. So 0 divided by 3 is still 0. So in an equation, if you divide both sides by the same thing, you don't have to write it as a factor on the outside. So x equals negative b, so that's negative 8, plus or minus the square root of b squared minus 4 times a times c, all over 2a. X equals negative b plus or minus root b squared minus 4ac, all over 2a, right? So what is this under the radical sign here, root sign? This is going to be what? 864 minus 48, which is what? 16? Somebody double check me? Yep.
64 minus 48 into my calculator, and it gave me 60. And I did it again,
60?
and it gave me 20. I'm not sure what's wrong with
Your calculator is messed up.
Your calculator sucks.
it. I got the right answer now.
Okay.
Brutal.
So what's a,
I'm very scared.
yeah, that's scary when your
Can't use
calculator
this
does
on
that.
tests.
So this is, excuse me,
Hold on.
what is this? 12 over 8, right? 12 over 8, which is what? 3 over 2? 1.5? What do you want to do? 3 over 2? 1.5? 3 over 2? And what's the other one?
1 over 2.
1 over 2. Okay, let's finish this one up. So, could we have two answers? Maybe. There's a good chance that one's going to need to be rejected for some reason. And what I would like you to see is that the length here, 3 minus 2x, if you did 3 minus 2 times 3 over 2, that would be 3 minus 3.
That's 0. It doesn't work.
0. So you don't want length of 0. So we're going to reject 3 over 2. So we're going to say x is 1/2. And if x is 1/2, that's really what we're looking for, I think. Find the largest volume. So if x equals 1/2, the volume is going to be equal to, what was that? Was it x? No, shoot. The volume was 3 minus 2x squared times x. 3 minus 2x squared times x. Or, so 3 minus 1, that's 2 squared times 1/2 equals 2. So the volume is 2, what are the units?
Centimeters cubed.
Meters?
Oh, meters.
2 meters cubed.
Beauty.
And I believe that's the correct answer. Yeah, 2 meters cubed. All right, so finish that 4.4 assignment for tomorrow, and I'll give you your hand-in assignment that you can start working on tomorrow. There it is.